This video is still part on proving limit theorems or for limit of the sequences. Still on the review on sequences and series, part in the preparation for real analysis. We are going to use here the definition of the limit of a sequence in proving this. We are to prove that the limit of the quotient of sequences a sub n and b sub n be equal to the quotient of their corresponding limits. We have L sub 1 and L sub 2 if L sub 1 is the limit of sequence a sub n and L sub 2 is the limit of the sequence b sub n. Here's the actual statement. Let a sub n and b sub n be convergent sequences of real numbers with the limit of a sub n be L sub 1 and limit of b sub n, which is L sub 2, which is not equal to 0, then the limit of a sub or the quotient of a sub n and b sub n is equal to the quotient of L sub 1 and L sub 2. Take note, there is a restriction here for the limit of b sub n being not equal to 0, so that our limit of the quotient of the two sequences also existing. So we are going to show here the proof of this following the idea that number one, we're going to construct the definition, the target for the definition, and then apply the necessary skills, properties in order for us to arrive to that. So the proof here will start by letting epsilon be greater than 0. Okay, because epsilon will come out later on as part definition. What we need to show is this. We must show that there exists n, which is a positive integer or natural number, such that if n is greater than that n, then it fits the definition that the absolute value of your quotient of your sequences minus the quotient of their limits is less than epsilon. This is our target. That's our end goal. If we could show that, then this is true. Again, for the limit or L sub 2 not being equal to 0. Okay, so that's what we need to do here. So what we need to do is to restructure this in such a way that these relationships will come out. If you're not yet familiar with that, the limit of a sub n equal to L sub 1 can be written by the definition into this form. Okay, and then for b sub n minus L sub 2 for this, of course they should be less than whatever will be the form of epsilon here. That's our goal later on, which will lead us to this. Okay, so what we need to do is again restructure this if we can. Note that once we combine them into one expression, you have a sub n over b sub n minus L sub 1 L sub 2 is equal to your LCD is b sub n L sub 2. So you have here a sub n L sub 2 minus b sub n L sub 1. Okay, that's the what they call this one, its form, right? So you have that on your form. Now we cannot simply break this because we cannot invoke here the triangle inequality or other forms for absolute value, because there is still a need for us to look for possibility of these two existing. We have the difference of a sub n and L sub 1 and b sub n and L sub 2, and it's here, it's not yet clear. So let me go to my next step. I would like to introduce here, okay, let me just use this portion first to save some space at the bottom. What if I have a sub n L sub 2 plus 0 minus b sub n L sub 1, okay, all over b sub 2 L sub b sub n L sub 2. I'm adding 0 here, which is a identity element for addition, but that is actually purposely placed there to introduce inverses, to which I can pair with these two, just like what happened in the previous video on the product of two sequences. You can also review that on your own time. The link is part of this playlist. So what we could do here is this. Okay, let me introduce a sub 1 L sub 2. Let me introduce here negative L sub L sub 1 L sub 2, but positive L sub 1 L sub 2, their product, minus b sub n L sub 1. Okay, I'm adding this, but they are just inverses of the other, hence they are just equal to 0. We are not hurting our expression. I'm just adding that so that we have here L sub 2 and L sub 2 I could take out. I also have L sub 1 and L sub 1 I could take out. Probably will help us later on look into the possibility of pairings needed for these two. Okay? All over B sub n L sub 2. So what happens here is this. Once I will take out L sub 2, I have A sub n minus L sub 1 plus I will take out L sub 1. I have here L sub 2 minus B sub n. But what we need is B sub n minus L sub 2. What I need to do here is this. Instead of positive L sub 1, okay, positive L sub 1, let me take out minus L sub 1. Hence, this would become, please bear with this, please be mindful of this. Once I take out negative L sub 1, is negative L sub 2, and this one will become positive B sub n, right? And then I could also rearrange this. Please bear with me. I'll be rearranging that. I will have this form. B sub n minus L sub 2. Okay? So, that is when I took out negative L sub 1 from this. So, I have positive B sub n. As I take out negative L sub 1 from this, I have negative L sub 2. I need to do that because that is what I need here. B sub n minus L sub 2. Nevertheless, that's just mathematical processes. So you don't need to stress yourselves about that one. Okay. Now, once I have this, I can now break this into two different forms. You have the absolute value of, of L sub 2 times A sub n minus L sub 1 over B sub n L sub 2 without canceling that, okay? Without removing that in the meantime. They have here minus L sub 1 B sub n minus L sub 2 over B sub n L sub 2. Okay? I'm not going to cancel that so that my denominators will be the same. My point of sharing this is, once I separate them into two different rational expressions, I can now invoke the triangle inequality. The triangle inequality allows us to say that if I have a difference, which also works for addition, actually the addition is what precedes the subtraction, but this works here as well. If you have the difference of two different expressions under absolute value, that can be written as less than or equal into individual absolute value notations, but the addition, we have here addition. Basically, it works on addition, but it also works on difference. So what I have here is L sub 2, A sub n minus L sub 1 over B sub n L sub 2, and then you have here plus L sub 1 B sub n minus L sub 2 over B sub n L sub 2. Okay, so that's triangle inequality. Why are we doing this? Because I can now finally use another property. Again, these are all just equal to this form, okay? This form, and we need to make sure that there is an expression less than epsilon. So these are all just derivations. Take note, this is product, this is also product. So I can now use as well the process of the product. Okay, the product or the absolute value of a product is equal to the product of the absolute value. So I have here, as I take out A sub n minus L sub 1, I have here L sub 2 over B sub n L sub 2. Okay, because this is just a product. When I pair this with that, that's just the product. Okay, it's also true here. Plus, you will have the form L sub 1 over B sub n L sub 2, and you have here the absolute value of B sub n minus L sub 2. Now, I would like to do this because this is what I want. I would like them to appear separate expression, because that's what I need here. Okay, in order for me to look for the proper or an appropriate form of your epsilon. Okay, now, to which I can still move further. Okay, let me deal into this. A sub n minus L sub 1. I could cancel this, right? Leaving, you have here 1 over 1 B sub n. Plus, I could also take out 1 over B sub n here and leave L sub 1 over L sub 2 for B sub n minus L sub 2. We will be using the same concepts as what we did on the product, as we were going to introduce certain m. because this is a sequence and this is a sequence, there is a theorem for that it's also bounded. So we can reintroduce another constant m, which states that there exists m greater than 0 such that, okay, such that absolute value of b sub n is less than or equal to m for all n integers. Okay, so with this, let me copy this. I will be moving to the next page because I don't have much space here. Copy, right, paste. Okay, also be copying the origin of all of this, or let me rewrite this one here. This, I'm talking about this one because this should appear on our next page. This is actually the absolute value of the quotient minus L sub 1 and L sub 2, right? So we are going to that. That would mean that in our form, we can have here a sub n minus L sub 1, 1 over m, or absolute value 1 over m is just 1 over m because it's greater than 0, okay? Plus also 1 over m here, and of course we can break this into two absolute value notations. You may or may not, but since they are exact values, so let's not deal with other representations. We just used m because this is actually a sequence, okay? Now, we were able to establish this. Our goal now next is to make sure that our end goal of epsilon will come out. So what we need to do is to go ahead with these two, with their individual representations, to make sure that we could have a proper expression for our epsilon. Here is how it goes. So since, right, limit of a sub n is equal to L sub 1, then, okay, take note of this. This is similar to what happens to our forms earlier dealing with the addition of limits or sequence. We have the difference of sequence as well. There exists n sub 1 element of z plus such that if n is greater than or equal to n sub 1, then a sub n minus L sub 1 is less than. This is where it gets tricky. It should be epsilon, right? However, take note, there are two of them. There are two of them. And in our previous discussions, especially in addition, difference, and product, we're able to make sure that this should be over 2 because there are two of them added. There are two of them. However, this is not enough because once you substitute that here, say for example, epsilon over 2, as you multiply with it 1 over m, there is that m will appear. In short, m will appear on the final form, but we don't need m here. We only need epsilon. So what we need to do is to introduce m on our numerator here. So the final form here is m epsilon over 2. Okay? So epsilon will be cancelled later. Don't worry about the 2 because it will also be cancelled later on together with its final for b sub n. So that's for that. And then also, limit of b sub n is equal to L sub 2, then there exists n sub 2 element of z plus such that if n is greater than or equal to n sub 2, then b sub n minus L sub 2 is less than. Again, we need over 2 to make sure that when added, it will become 1. We also need epsilon here, but what we need more is also m here because we also have 1 over m, but we have the absolute value of L sub 2 over L sub 1. That's 1 here. Why? So this would also be cancelled. And since L sub 1 and L sub 2 are exact because it converges to that value, so we simply need that. Okay? So take note of these two expressions. So they really depend on what is your form, if you're using triangle inequality and so on and so forth. So what we need to do here finally is take, because we introduced n sub 1 and n sub 2, let's use n be the maximum of your n sub 1 and n sub 2. Then if n is greater than or equal to n, the maximum of these two. So we already discussed that concepts. Now let's review everything. You have a sub n over b sub n minus L sub 1 over L sub 2 is less than or equal to, using your triangle inequality, this one here. So I can just copy that to save some time. Copy, paste. I am pasting it here, but I'll be doing this. Okay, so I'll be erasing this as well, and that. Okay, now this is what is the form that we have made earlier, and then using these representations, we have this one which is less than m epsilon. So this is all less than m epsilon over 2 times 1 over m, right? Plus 1 over m here. Then you have the absolute value of L sub 1 over absolute value of L sub 2. And then this one is here. You have times m epsilon over 2, absolute value of L sub 2, absolute value of L sub 1. Okay? Okay. So, now, as we cancel everything, this is equal to, cancel that, epsilon over 2 plus, cancel m, L sub 1, L sub 2, also epsilon over 2 equal to your epsilon. Okay? So, as you have something like this, we have now shown that the absolute value of a sub n over b sub n minus L sub 1 over L sub 2 is just less than epsilon. Take this, take that, take this, so you have this form, and this is actually the end goal or the end product that we need to achieve to invoke that this is true. Okay? So it really needs a lot of concepts and strategies for you to be able to master this. So you can review this on your own time, re-answer this or redo this on your own time. But since I am done here, so since epsilon is greater than 0 is arbitrary, then we conclude that since we have shown this, the limit of the ratio of a sub n and b sub n as n approaches to infinity is equal to the ratio of L sub 1 and L sub 2, given that L sub 2 is not equal to 0. This ends the proof. Okay? The proof for the limit of the quotient of convergent sequences. Thank you very much for watching.